Okay, so in this chapter, we're going to talk about the atom and parts of the atom. So first of all, we're going to start out with a little bit of historical context. Then we're going to talk about Dalton's atomic theory, and we're going to finish up this conversation with a couple laws that fall out of Dalton's theory. So, all right, so first of all, let me make sure I got my marker here going. Red, no, let's do red. The concept of atoms was first brought up by the Greeks. Okay, Aristotle thought that matter consisted of various combinations of the four elements: earth, wind, and fire, and water. And then finally, this is a long time ago, right? This is before Christ. This then is obviously not too long ago. John Dalton, a school teacher, proposed his atomic theory, and there's 5 parts of Dalton's atomic theory, and they go like this. First of all, matter is composed of exceedingly small particles called atoms. Sounds like the Greeks. An element, now this is new, an element consists of only one type of atom, and that each one of those is the same as all the other atoms. Okay, element consists of only one type of atom. So an example of that is a copper coin, pre-1982, because we started using zinc on the inside of copper because of pennies, because copper is too expensive. It's worth more than a cent, right? So there are a bunch of little copper atoms inside a copper coin, if it's completely copper, right? And there are about a little bit less than a mole, about a 20th of a mole of copper atoms in a penny. All right, and they're all the same, and they're all stacked in there, and no matter where you go, you're going to find a little chunk of copper atoms, right? All right, so that's the first and second one. First of all, matter is composed of atoms, and an element consists of only one type of atom. Okay, now the third thing that he proposed was atoms of one element differ in properties from the atoms of other elements. They differ, okay, because they're atoms of one particular element. Fourthly, a compound consists of atoms of 2 or more elements combined in small whole number ratios. Sounds like the law of definite proportions. A compound consists of atoms of 2 or more elements combined in a small whole number ratio, which we already defined that term in a previous conversation, right? And then finally, atoms are neither created nor destroyed in a chemical change, but instead rearrange, right? So they're neither created nor destroyed during a chemical change, and that's true, all right? They are created or destroyed in physical changes, right? Like a nuclear reaction, but in chemical changes, no. All right, so those are the 5 postulates of Dalton's atomic theory. An example is looking at copper oxide. Copper oxide's black, right? Why is it black? Well, it's not a blend of the red and the brown, by the way. This is an artist's conception. Oxygen atoms are not red, and copper atoms are not brown. They are brown when you get a bunch of them together, but in an individual copper atom is not going to be brown. It's too small, right? It's smaller than color. So copper oxide can you see this is combined? It looks like it's a 1-to-1 ratio. There's one, there's another one, there's another one, there's another one, 1-to-1, right? So Dalton's atomic theory says that compounds are going to combine atoms in definite ratios. Right? Another picture of that might be, you've got a picture of copper here in a bottle, and there's oxygen also, right? See, there's oxygen in the bottle, and there's copper. And it's brown, right? Brown and transparent. But when they combine, they're black, right? All right, so let's look at the laws that these introduce. First of all, the law of conservation of matter. We brought this up in a previous conversation, but Dalton's atomic theory gives some explanation for this. If elements are made up of little pieces called atoms, then when you have a chemical reaction, they just rearrange, right? So you're not going to lose anything or gain anything. So the law of the conservation of matter is explained by Dalton's atomic theory. The law of definite proportions is sort of like one of Dalton's postulates, right? All samples of a pure compound contain the same elements in the same proportion. All samples of a pure compound, or pure compound, contain the same elements in the same proportion by mass. Okay? So Joseph Proust, a French chemist, did experiments to show this. He took isooctane. Okay, he took a 15-gram sample. I'm sorry. He took a this is not 15. This is about a 17.5-gram sample. Broke it down. Got this much carbon and this much hydrogen. Then he divided 14.282 by 2.78 and got 5.33. Then he took another sample, maybe a 26.5 gram sample. He got 22.33 grams of carbon and 4.19 grams of hydrogen, right? You divide 22.33 by 4.19 and you get 5.33, right? Then you took another sample, which was about, a 23 gram sample, right? And you got 19.4 and divided it by 3.64, you got 5.33. So this is an example of the law of definite proportions, that when you take a pure compound and you divide it up, you're going to get the same proportion. Okay, and finally, the law of multiple proportions. The law of multiple proportions states that when two elements react to form more than one compound, two different compounds, right, a fixed mass of one element will react with the masses of the other element in a ratio of small whole numbers. So let's look at an example here, and this will make more sense. So first of all, we've got these two compounds that are copper and chloride, right? Copper and chloride. This is going to be I don't even know. I think it's copper chloride, and this is that's not true. This is copper chloride, copper 1 chloride, and this would be copper 2 chloride. Okay. Not that it really matters, but you've got these two compounds, right? So you've got two elements, and they combine to make two different compounds, copper 1 chloride and copper 2 chloride. Okay? And they have two different colors, right? They're two different compounds. Well, when you find their ratios, when you divide their ratios, or take the ratio of their ratios, you get small whole numbers. That's what the law of multiple proportions says. All right. That's it for this conversation.